I'm Chanda Devnath. The PMRF, I have got my PMRF the last December. So I'll continue my session of the reactive intermediates carbene and nitrene. Previously, I have taken two sessions. Those videos have been uploaded in the on YouTube, my YouTube channel, which is Chanda Devnath PMRF NPTEL TAship. If you want to watch that, you can go and access. And anyway, the link and the slides of those two classes have been uploaded in the NPTEL site. I think NPTEL people have given you the access to see those videos and the slides. So this is the previous week I have given you two tasks to solve. First one is this and second one is this. So I have told you that I will solve this in the next week. So whoever has completed these two is all the very good. So for those who are unable to solve, or somehow for some little reasons they couldn't get the answer properly, for them I will solve this question. So let's start. Okay. So in the last session I already have taught you about the wolf rearrangement. You may have know that what is wolf rearrangement. Still I will try to explain that again. So according to wolf rearrangement, when it will be when light is radiated on it, N2 will remove from the system and it will generate a carbene intermediate. It will generate a carbene intermediate like this. Here it will be carbene. It will be a carbene intermediate. Then it will undergo wolf rearrangement. What is wolf rearrangement? This will go here and this bond will shift from here, giving us a ketene like intermediate. This type of intermediate we will get. We will get this type of ketene intermediate, and this group will be as I'm writing this is R. This one I'm writing this group as R. So here then, as in medium, methanol is there. So then methanol, for methanol, this oxygen will attack here and go up and down. As this, all this I have been discussed in the last class also, giving us this product. Okay, I think everyone has understood, and I think everyone has already solved. Still, for those, for check your answer, and for those who somehow there is some issues, and it will be as also revise also about the wolf rearrangement. In the same way, this will be also a wolf. This will also wolf kind of rearrangement. What will happen by this one? This will called by this is a chlorinating reagent. From this one we will get acyl chloride here. We will get this will turn into acyl chloride. This will turn into a, I am just writing this as a R group. This total group I am writing as a R. This total thing I am writing as a R. I am writing as a R. So R COCl will get acyl chloride. R COCl will get and when this diazomethane will be added, we will get this type of complex. We'll get this type of complex, which will generate, which will undergo Wolff rearrangement to give us this type of Wolff rearrangement, and it will give this product like the before. Okay, I think you can note the answers, as I didn't show those answers in the last slide, so you can note these answers for now. So this will like Wolff rearrangement. Both of are Wolff rearrangement. Both of them are Wolff rearrangement. Both of them are Wolff rearrangement. So come to the next thing. So I was teaching you have some name reaction involving carbene. So I'll continue that. So I already have taught you maybe 2 or 3 name reactions already. So this one is left, one thing. So that is Reimer-Tiemann reaction. In this reaction, as you have seen that it occurs through alpha, the reagent is, what is the reagent of the reaction? This is the reagent of the reaction, chloroform and base. Chloroform and KOH. Usually chloroform, and it is come from usually chloroform and KOH or NaOH. KOH or NaOH. So what will happen? This will undergo alpha elimination. I have taught you all these things. Through alpha elimination, it will generate a carbene intermediate. It will generate a carbene intermediate. Then when you are adding any aromatic compound like phenol, they have added, they have used phenol. So when we are adding phenol, as in medium base is there, so we will get phenoxide ion. Then through electrophilic substitution, aromatic electrophilic substitution reaction, there will be a ortho attack here, because this type of carbene are electrophilic in nature. So there will be a ortho attack, and through aromatization, it will give this type of intermediate. This type of intermediate. So in medium, we already have OH minus. So when there is 2 chlorine atom, so this chlorine atom will be substituted by the OH atom, substituted by the OH group, substituted by the OH group, and giving us this type of compound. 1 Cl, this OH will attack here, and 1 Cl will get removed. We'll get this one. Then again another. Then this O minus is still there, so O minus will abstract the proton, and it will come here, and another Cl will get removed, and we will get this type of aldehyde, orthoaldehyde. See, we will get this type of orthoaldehyde. So the speciality of the reaction is this: in this reaction, we will get ortho product as a major. We will get ortho. This, we all know that OH group is an ortho para directing group. From OH group electrophilic substitution reaction, aromatic electrophilic substitution, we will get ortho. We usually get, where is my cursor? We usually get mixture of ortho plus para, and in most of the cases, due to less steric hindrance, we get para as the major one. But here specifically in this Reimer-Tiemann reaction, we get ortho as a major. We get ortho as a major. We get ortho as major. Why? Because see here there is, after the formation after this electrophilic substitution reaction, there is a chance to get stability. There is a chance to formation of hydrogen bonding. There is a chance to formation of hydrogen bonding. Due to this, the ortho product we get in a major portion. So reason, due to H bonding stability, due to H hydrogen bonding due to hydrogen bonding due to hydrogen bonding. So due to hydrogen bonding here, we get the ortho product as a major. So let's come to the next. So it's this one. So here you can see I have taught you I have explained this question in the last session, like when you are adding this any trimethylamine reaction in the phenol, there is a para substituted phenol, we will get. So here you can see the para position is already occupied. Here the para position is already occupied. So the only option is ortho. So we will get orthoaldehyde. We will get a orthoaldehyde. And as I have told, this is a Dakin reagent. Through Dakin rearrangement, we will get this one. So if anyone wants to know what is Dakin reagent, you can go and check in Google or in some books also. This is given. This is a famous reaction. So in books or in Google even, you can check the mechanism of the Dakin reagent. It's through a transition state, is a large transition state. So this is not part of this class or this course, so I'm not explaining that. But if anyone is interested or anyone want to know, they can ask me in the comment section or anywhere. So I will try to explain that in the next session if anyone wants to know, or I will try to provide the mechanism if anyone wants to know the mechanism but can't. So tell me in comment section or any feedback section, I will try to solve that. So let's come to the asymmetric cyclopropionation reaction. So here you can see by using a chiral ligand we can get a asymmetric cyclopropionation. What they are saying? Asymmetric intermolecular cyclopropionation reaction have been reported with a variety of metal ligand complexes. The best choice of complex depending on the structure of the substrate. Here the bicyclic lactone was formed with high inertial selectivity using the chiral rhodium complex. So by using this chiral rhodium complex, we can get the cyclopropionation reaction through high inertial selectivity. With high inertial selectivity, this reaction was used in a recent synthesis of the chiral cyclopropene until cyclopropene unit in the antifungal antibiotic ambrutecin S. So come to the next thing. So epoxide or aziridine formation. So it can be promoted by trapping the carbene with a sulfide to give a intermediate sulfur halide, which then adds to an aldehyde and imine. What they are saying? See, like the previous things, when this rhodium catalyst, rhodium 2 catalyst is added, N2 will get removed and giving us this intermediate, giving us this type of carbene intermediate. Sorry, it will be this type of carbene intermediate. Will get this type of carbene intermediate. So this carbene, as we know, carbenes are electrophilic in nature, and sulfur is the electron donating group. So this sulfur will attack to this carbene center. Sulfur electron will attack to the carbene center, giving us this type of halide intermediate. This is a sulfur halide because there is a two positive and negative charge adjacent. Sulfur is a positively charged and there is a negative charge adjacent to the positively charged sulfur. So this is called a sulfur halide. So we are getting a sulfur halide. So when we will add a, so this type of reaction I have taught you previously in the first session maybe. This type of sulfur halide also we can call this as a sulfonium halide. This is also called as sulfonium ion. Sulfonium. Sulfonium. Sulfonium ion. It's also called sulfonium sulfonilamide. Sulfonilamide. So when sulfonilamide is added to a aldehyde, what we will get? We get a epoxide. This I have been taught earlier also. So what will happen? So if we consider this as a this one, right? Like this, if we consider like this, so what will happen? This negative charge will attack here, and this positive charge meter, and we will get a epoxide ion. We will get a epoxide as a product. So I have taught you earlier also. You can go and check there. So whenever a sulfonilamide is added to a aldehyde, we will get a epoxide. So here we can get this type of, so addition of a tetrahydrothiophene to a rhodium carbenoid generated from a phenyl diazomethane gave a ylide which adds to the benzaldehyde to give the trans epoxide in the high yield. So we are getting the trans epoxide. Why trans? Because see, phenyl and both the phenyl group are anti to each other. So it's a trans epoxide selectively. So the ylide formation can be used to good effect for a variety of transformation. With an allylic sulfide, the resulting sulfonium ylide undergoes 2,3 sigmatopic rearrangement. This type of rearrangement can be effected with allylic amine, ethers, and even allylic halide. So what is the thing? So what will be happen by this copper catalyst? Again I lost my cursor. Ah, ah. So when this N2 will get removed, and this there will be a carbene system, so this will attack here, giving us there will be a plus and there will be a minus. So the intermediate will be like this kind of. I'm trying to draw as much I can. So just consider this as a group. So there will be a plus, negative charge, and then it will go a 2,3 sigmatopic reaction. What is 2,3? See, if we do the numbering 1, 1, you have learned maybe 2, 3 in a pericyclic reaction. So it is 2, 3. So it will be a 2, 3 sigmatopic reaction. What will happen? This bond will go. This bond will go here. This will attack here. Shift and giving us this as a product. Okay, I think everyone has understood. The next, let's come to the next one. What is intramolecular capture of a metallocarbene generated from a diazocarbonyl compound is a useful method for the formation of a cyclic carbonyl halide. Cycloaddition is the effective with alkene, carbonyl or other dipolar file and leads to the Binch bicyclic compound. So in this example you can see what they are saying. So if there is a whenever there is a metallocarbene, so after the N2 elimination, there will be a metallocarbene because rhodium will be here. So a metallocarbene generated by the diazocarbonyl compound. So this metallocarbene is useful for the formation of cyclic carbonyl halide. So instead of, as there is a sulfur, instead of sulfur, there is also oxygen atom. See, ester oxygen atom. So this extra oxygen atom will attack here and giving us this type of carbonyl halide. This is called carbonyl halide. It's called carbonyl halide. So this is called carbonyl halide. So carbonyl halide, and this will undergo a cycloaddition reaction. See, 1,3 dipolar cycle is 1, 2, 3. There is a 1, 3 is 1, 3, and there is a 2 plus. So there will be 1, 3 dipolar reaction. What will happen? It will go here. So there will be a 1, 3 dipolar cycloaddition reaction, giving us this as a product. Okay. So what is happening after carbene generation? We are forming the ylide. So if there is an electron donating substituent is there, so they will donate and a ylide will be formed, and that will undergo through a pericyclic reaction. It's famous something like one is 1,3 dipolar cyclo addition reaction, and that was a 2,3 sigma topic reaction. So it will go through a pericyclic. So it is a 1,3 1,3 dipolar. It will be a 1,3 dipolar cyclo addition reaction. 1,3 dipolar cyclo addition reaction. Okay. So based on this, let's solve this question. So what they are saying is a synthesis of pine beetle pheromone exo and endo makes use this story makes use of the following reaction. So draw the structure of the intermediate ylide and explain the regiochemistry of the cycloaddition reaction. So let's solve together. So what is happening? You guys, I am also solving. Whoever is watching this session or some, so you can also try this session along with me. So let's solve together. So what will happen by the similarly by this rhodium plus 2 catalyst, N2 will get removed. One sec, I will just check this recording is happening or not. So a synthesis of so what will happen? The N2 will get removed from here, and it will generate a carbene system. Generate a carbene system. As like before, as there is a carbonyl system, oxygen is here, so this will donate here, giving us a ylide system, giving us a carbonyl ylide, giving us a 6-member carbonyl ylide, giving us a 6-member carbonyl ylide. So now when this is ethylaldehyde will added this why is it? So it will be added. So they said explain the regiochemistry. What is regiochemistry? So regiochemistry is when a substrate choose between two reacting center, what like regio state. See, so what they are saying. So when the aldehyde is added, so it can add it to this 1,3 dipolar product by like this, as similar like this, like one will be from here and one bond will from here. Also that can bond from like here, like in the cross from here. I will show in the different. So one it can join in the reverse way also, like this will join here and this will join here. So what is the regiochemistry of here? Like which center will join to the which center? So we can see this center is negative, and we all know in for aldehyde compound this carbon is more electropositive because of the resonance. This is more electropositive. So what will happen? So this will attack here and this will go here. Okay. So this will leads to this product. Okay. Understood? So I will just erase the wrong combination. So we will get this type of product. So like similarly, there are some examples for this similar kind of elite formation. So what will happen here? This the same everyone just you know the same thing is happening again and again. So the N2 will get removed. This N2 will get removed. It will there will be a carbene system. Then it will add. Then this carbonyl group will add here, giving us this type of elite system. And when there is a double bond, so there will be a 1,3 dipolar cycloaddition reaction. So there will be a 1,3 dipolar cycloaddition reaction. Okay, this will be our product. Similar reaction will happen here. There will be a carbene. Again, this will attack here, giving us a carbonyl elite, and there is a triple bond. So after cycloaddition also there will be also remaining a double bond because it is a triple bond. So whenever you are solving problem, just check there is a triple bond. So after cycloaddition also there will be remaining a double bond. There will be a double bond remaining. So in the next reaction, I will just remove this. So in the next reaction, again there will be a carbene system. This carbonyl will add here and it will add to this double bond, giving us this type of product. If you want to know the mechanism, you guys can. I am not showing because I don't have pen here, so cursor is a bit problematic to draw this type of this large structure. So you guys can try the mechanism. I believe that if you try through a pen and paper, it will give you more understanding to do some unknown problems or anything. So just don't based on the videos or the slides. Just whenever you're watching the slides, just take a pen and paper along with the videos. Just try to solve the questions also. This will help you. I think this helped me. So whenever you are solving some problems, so keep a pen and paper and try to solve those questions along with the videos or the slides. So there's a next reaction. What is happening here? The allylic ethers and acetyls can react with carbenoid reagents to generate oxonium elide, which undergo 2,3 sigmatopic shift. What they are saying? 2,3 sigmatopic shift. So what is happening? Whatever was happening here, there is just happening as an intermolecular. So after this N2 elimination, this there this ether, this ether oxygen, this ether oxygen will attack here. Sorry. This ether oxygen will attack here and giving us this type of elide, oxonium elide, this type of oxonium elide, which will undergoes a 2,3 sigmatopic reaction. What is 2,3? If you count 1, 1, 2, 2, 3, it will undergo 2,3 sigmatopic reaction. What is happening? It will go here. This will come attack here. And this will attack here. And this will go here. Okay. So they have already shown by pen. I will just remove my it will be too congested. Okay, I think everyone has understood. So let's come to the next reaction. With carbene centers adjacent to a double bond, usually cyclized to cyclopropene. So after, so this is a, after, this is a sulfur through sulfoxide elimination, there will be the ylide will form here. There's a carbene will form here. So then the carbene will add up to this alkene. Will add up to this alkene, giving us the cyclopropene kind of ring. Understood? This everything will remove like Bamford-Steven reaction. This is a Bamford-Steven reaction. So Bamford-Steven reaction, it will get removed and the carbene will generate here and it will get add up here. So it is a example of kind of Bamford-Steven. I have explained this in the last session. You can go and watch or see the slides. Comfort. So through Bamford-Steven reaction, there will be a carbene will generate here and this carbene will add up to this double bond, giving us this type of cyclopropene ring. So again, the cyclopropylidene undergo ring opening to give a alene. The reaction that would be expected to generate a cyclopropylidene therefore lead to the alene and often in a preparatively useful yield. Sorry, there is some typing mistake. I again lost my cursor. So it will be useful. It will be P. Usefully. So what is happening after this one? After this elimination, we will get a carbene intermediate, which will undergoes a rearrangement, giving us a alene system. What is happening here? This will go come here, and we will get a alene kind of moiety. So next is types of carbene. We already have learned the types of carbene based on their structure. One is singlet, another is triplet. That is based on their structure. So we all there is a, now we will explain the types of carbene based on the metal carbon bond, the nature of the metal carbon bond. So in previous examples, the formation of the carbene is initiated by metal like copper, rhodium, silver. All the examples I have seen, I have shown you like one metal we used to use. So the carbene intermediate in that one also metallocarbene used to generate. Like if I was all everyone every time I was saying that the by the action of rhodium plus 2 catalyst there will be a generation of metal carbene intermediate like which will be coordinated with the rhodium ion. So again the carbene intermediate this in the this reaction are formed the metal carbene intermediate form, but these are as reactive, but here that those like rhodium carbene those are that those metal carbene was getting formed, but those are reactive. So just like in the this type of reaction, so whenever they are forming they will just react because after this carbene generation this will react so fast, so we can't isolate this metal carbene intermediate. So after this rhodium will eliminate the N2, this will remain as this type like this, as N2 is getting removed, so it will stays as this. But here this bond is weak and this is so reactive that it will attack then it will react so fast we are not unable to isolate this metal carbene complex. But here in some cases this metal carbene complex are extremely stable, so stable that we can isolate them and store them for months. So for example, the decomposition of phenyl diazomethane in presence of a ruthenium 2 complex gives the carbene complex stable enough to be isolated and stored for a month. What does the phenyl diazomethane, after, as you know, the after N2 elimination we will get this type of carbene. When we are adding this when in this carbene we are adding this type of ruthenium complex, we get this one, and this is stable. This we can store, we can isolate that, we can store that. So this and we can use this carbene in different kind of reaction. So the next is, so based on this metal carbon, so this type of metal carbon can be formed. So now this metal carbon bond can be in different type in this carbene. See, a metal or carbon bond is there. So based on the nature of this metal and carbon, the carbenes are divided into two types. One is Fischer carbene, one is shock carbene. What is the characteristics of Fischer carbene? In case of Fischer carbene, the carbene generated, it is singlet and it is electrophilic carbene carbon. What they are saying, that this carbene will generate after this metal elimination or something, the carbene generated here, the carbene generated here, um, the carbene generated here, this is singlet and this is electrophilic. What the nucleophile will attack here, the nucleophile will attack here, this is singlet and nucleophile. But in case of shock carbene, this carbene is triplet, and as it is triplet, it is nucleophilic because it acts as a free radical. Because you know that in case of triplet carbene, both the electron are in different orbital, so they act as almost as a free radical. So this can be act as a nucleophilic carbon. So they can attack, they can donate one electron to some electrophilic species. So in case of Fischer carbene, it acts as electrophilic carbene and singlet carbene. In case of shock carbene, it acts as nucleophilic carbene and as a triplet carbene. In case of Fischer carbene, it acts as a pi acid. As it is electron deficient, as it is getting attacked by nucleophile, it is electron deficient. So as electron deficient, it is pi acid, and it has to be the substituents on this carbene atom. The substituents on the carbene atom has to be pi donor. It is pi. So this, so in this case, the metal, the carbon will be positive and the metal will be negative. So to stabilize the metal charge, to stabilize the negative charge on the metal, the ligand on the metal has to be pi donor. Sorry, it will be pi. Sorry, there is a printing mistake. Should be substituent on the metal has to be pi acceptor. It has to be pi acceptor. Has to be pi acceptor. There is a some. I have done some mistake. Sorry. Has to be pi acceptor. Why pi acceptor? To stabilize the negative charge on the metal. So this, it will be delocalized through the ligand. So the carbonyl, that type of system will be there. It should be connected to the metal to stabilize the negative charge on the metal. So, but in case of this one, this act as a pi base. So in case of shock carbene, as this is negative, it acts as a pi base, and substituents are not be substituents are pi donor. See, it will donate the electron. So in case of Fischer carbene, the metal usually molybdenum, chromium and tungsten. And in case of shock carbene, the metals are usually titanium, tellurium, tungsten and ruthenium. So in case of Fischer carbene, there is a competitive resonance is there. So what is happening in case of Fischer carbene, there is also some electron donating group like OMe or something. So these will donate electron here, and again the metal carbon bond. So this there will be there is a carbonyl there is a double bond which can delocalize through the carbonyl, which can delocalize through the carbonyl. Delocalize through the carbonyl. Because of this metal carbon bond is longer. Because of this, the metal carbon bond is longer, but instead of is less longer. What I am saying, it is shorter. Comparatively, it is shorter. Okay, understood? Next is cyclopropanation. So in this type of metal carbene can take part in different kind of reaction. So I will explain one by one. So first is cyclopropanation. The addition of chromium carbenes to the to the alkenes can be used to effect the cyclopropanation to give substituted cyclopropanes. Thus addition of excess 1-hexene to the chromium carbene gave the cyclopropane as a mixture of diastereomer with the isomer predominating. What they are saying, this type of chromium carbene when we are adding to this type of alkene system, simple cyclopropanation reaction that we have explained again and again, there will be generation of carbene and simple cyclopropanation reaction will happen. Next is Tabbe reagent. So what is Tabbe reagent? So when we are adding aluminium trimethyl aluminum to a titanium complex, we will get this. This is called Tabbe reagent. And when we added base, this will undergo a rearrangement, giving us this type of. This will undergo this type of rearrangement. It will go here. This will go here, and giving us this type of carbene system. So we have learnt in the last slide, titanium is a shock carbene. What is that? Titanium is a triplet carbene. You have learned. So this type of carbene system, when you are adding to a carbonyl complex like aldehyde, ketone, ester, amide, what is happening? This type of cyclic intermediate will form, like cyclobutane intermediate will form, and that will again undergo rearrangement to bond breaking. It will give us this type of compound. What is happening? The carbonyl oxygen is replacing by this carbonyl oxygen is replacing by CH2. The carbonyl oxygen is replacing by CH2. So it is comparable with the reaction which you guys have learned this reaction. If I'm giving you 1 minute, just remember this is comparable. The same product from the same substrate, we can get this product. In which reaction? You have learned that reaction. That is Wittig reaction. So you have learned that from aldehyde to alkene we can get through Wittig reaction. But the drawback of the Wittig reaction, or the not drawback actually, the limitation of the Wittig reaction was that was only for ketone and aldehyde system. Ester or amide system can't be take part in this type of oxygen transfer to the CH2. This type of reaction through Wittig we can't get this type of product. From ester or amide fluidic we can't get, but here in through this Tabbe reagent, all this type of compound, all this type of carbonyl compound, aldehyde, ketone, ester, amide, everyone can react with the Tabbe reagent, giving us this type of alkene as a product. So this is the advantage of the Tabbe reagent. So it is comparable with the Wittig. comparable with Wittig reaction. Comparable with Wittig reaction. But the advantage is this can take part in, but in Wittig part, in case of Wittig only Wittig is only aldehyde, aldehyde and ketone. Aldehyde and ketone. Understood? This is the advantage of Tabby reagent. You guys can check once. Next is alkene metathesis. Next is alkene metathesis. So what is alkene metathesis? Olefin metathesis has emerged as a powerful tool for the preparation of cyclic organic compounds. This type of olefin metathesis? What is metathesis? Metathesis means that the what is metathesis? One is ring closing metathesis, one is ring opening metathesis. So here, now first we are now like in this here we are just explaining about the ring closing metathesis. What is ring closing metathesis? The two olefin will join with each other. Two olefin will join with each other. So this olefin metathesis has emerged a powerful tool for preparation of cyclic organic compound, which can be like some organic compound which are impossible to form, like some alkene is like there is a or huge ring that is unable to form, but through this metathesis process we can form this type of cyclic alkene. So in case of metathesis involve the redistribution of carbon-carbon double bonds in the presence of metal carbene complexes. The reaction of this metal carbene with the alpha with the orthodine leads to the well defined carbocyclic system in what is termed ring closing olefin metathesis. What they are saying that in case of ring closing metathesis, this type of if this type of moiety is there, if this type of diene moiety is there, so this diene will join with each other and giving us this as a compound. So interesting. So what is the mechanism of this compound? So first see, as a catalyst in this reaction, as this metallocarbene catalyst, metallocarbene complex, we use this we may use these three catalysts. Among these, this is highly used, but when this can be used for you to steady caution, these two can be used. But comparatively, these two called Graf's catalyst. Graf catalyst has more functional group tolerance than that of the shock catalyst. So Graf catalysts have more more functional group tolerance than those than the shock catalyst. And both the scientists Graf and Shock was got Nobel Prize in 2025 2005 for this alkene metathesis. So both of them got Nobel Prize. Both of them got Nobel Prize in 2005. Both of them. Both. So what is happening? So this first we are adding this type of metallocarbene complex. See here, this type of metallocarbene complex. and it will form a cyclic intermediate with the first carbene, and then through elimination process it will get removed like this. It will get removed, giving us this again. This will add up to the another alkene and giving and this will be a cyclic process. Understood? First, this metallocarbene will add to an one carbene system. Then through elimination, we'll get a modified metallocarbene complex that will add up into another add up to the other metallocarbene complex. So, for example, here what is happening? We are adding this catalyst, which is catalyst A, that Groff's catalyst, first generation. So we are adding this catalyst, and so because this n number of carbon is there, so because of this, these two carbene, these two alkene will join. So there is a trick to do this reaction. Just join whenever you are seeing this Grubbs reagent. Just join two double bond. See this the this these two carbene, these two will get removed and these two will join. These two will join and giving us this as a product. So the next reaction is, so what is happening? So first we are adding this type of ylide complex. This is a ylide Wittig. Everyone know phosphorus ylide. So what will happen? This is a lactone kind moiety. So it will come here. So a aldehyde will be generated, and then by Wittig reaction, this aldehyde will be transferred to a alkene system. By Wittig reaction, this aldehyde will transfer to a alkene system, and when we are adding this Grubbs catalyst, these two alkene will join. See, the functional group here will be unaffected by the ruthenium. There is a functional group tolerance, high functional group tolerance. In presence of ester hydroxyl, this ruthenium can react. It won't be quenched by the hydroxyl group. So what is happening? Understood, everyone? What is happening? This will go here and this will open. So it will give us this type of moiety. This will give us this type of moiety. Aldehyde will be there. And this is a Wittig. Through Wittig reaction, we will get this. And when we are adding this Grubbs catalyst, these two alkene will join. Next is ring closing is metathesis is an excellent strategy for the synthesis of spirofused complex. So we know that spiro complex formation is bit tricky and difficult because this, see, the 4 carbon bond you have to form, and this 4 carbon bond you have to, and this is bit strain. There is a high strain is there. So forming this type of spiro compound is bit difficult, but by using this type of Grubbs catalyst, we can form spiro compound very easily. You just by this thing, this these two double bond will just join. Here, how it will getting joined? These two, there's an n number of double bond. So by just when this is n equal to 1, when this is n equal to 1, this and this will join, and this will join. It will give us 2 cyclopropene ring, fused cyclopropene ring, and when this n equal to 2, we'll get 2 cyclohexene ring, fused 2 cyclohexene ring. Understood, everyone? How it will getting joined? These two are joining and these two are joining. Understood? Just check. I am giving 1 minute to just understand. Next is this one. So again, by using 10 mole % of this Grubbs catalyst, we'll get these two alkene will cyclize, giving us this compound. And when this is called this, sorry, everyone knows about this reagent almost. This is hydrogenation reagent. So by this hydrogenation reaction, this double bond will get reduced, and when we will add LiLH4, this amide will, as the amide center will get, transfer into the CH2 amine. Amide will transfer into a CH2. So this has been done by this reagent, and this is has been done by this reagent. Understood? Both are reduction, but hydrogenation reaction, this H2 palladium is only effective on the double bond, and LiLH4 only effect on the amide or carbonyl system. So amide will transform into the amine system. So the next is, in cases where the metathesis with the catalyst A is unsuccessful or very sluggish, then the shock catalyst B or the catalyst such as C are often effective. And this is particularly the case for the formation of tri or tetra substituted alkenes, which are normally too hindered to be formed using catalyst A. What they are saying, whenever like the catalyst A can't are unable to get or very get the product or very slow reaction, then we add the other two catalysts. So here by using the it will be catalyst C and it will be catalyst B. It will be catalyst B. So by adding these two catalysts, we'll get the same kind of product, alkene metathesis. So these two double bond will join and giving us this type of cyclohexane ring, and here these two double bond will join and giving us this type of cyclooctane ring. So now you can count the number 1, 2, 3, 4, 5, 6, 7, 8. So these two center will join and giving us this type of cyclooctane ring. Next is synthesis of heterocycles. So by this Graf's catalyst, because of its high functional groups tolerance, it will also can give heterocycles. See here, this type of cyclic ether or cyclic amine kind of system can be generated. So similarly, this in the same way, these two double bond will join, and here these two double bond will join. Here see, this is presenting as a salt. Still the carbene will form. So this so much, the reagent is so much reactive that not this type of, in this type of ionic system also this will react. So next is large ring synthesis. Most reliable methods for the formation of large ring system. Large catalyst, because we all know the formation of the large catalyst be difficult through normal chemical method, because after 5 and 6 the rings get destabilized. Medium ring 7 to 9 can also be formed, but after that it's bit hard. So it, through this Graf's catalyst we can form the very large rings also, and it may lead to the mixture of EZ, but generally we get E as a predominant product. So here you can see these two double bond is joining, and we are getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. A 15 member ring. Whereas in case of this one, we are getting almost a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 21 maybe. 21 member ring, and we are getting E as the major. See? E as the major. Why E major? Because we know that the trans, in case of large ring, the trans are more stable because they can rotate the ring bond. In case of small rings, there is a high strain. We are trying to form a trans linkage, but in case of large ring, as there is a flexibility, so they can arrange to get the E stereochemistry. Next is in-ine metathesis. When an alkene reacts with an alkene, the result is two new alkenes. But when an alkene reacts with an alkyne, there is still a single bond remaining with the original alkyne, which ends up linking to two products together as a diene. So in case of in-ine metathesis, these two alkene system will just join. These two alkene system will join. But in case of alkyne, there is two alkene systems. So one will join with this alkene, but there will be also a remaining alkene system will be still there. Remaining alkene system will be still there. So what is the mechanism? First, the ruthenium complex will adapt to this alkyne system. It will break and giving us this type of cyclopropane kind of ring. One will be ruthenium complex and will be normal. Then that ruthenium complex will add to another alkene system and giving us this type of butadiene moiety. Giving us this type of butadiene moiety. So here are some examples. So what is happening here? When after this ruthenium complex will give this type of moiety. It will give this type where one will be connected to ruthenium steel and one will be a double bond. Then these two double bond will rejoin to give this type of product. This type of product is like butadiene. Since butadiene is there, so it can, if it can take part in Diels-Alder reaction, giving us this type of compound. This is the application. Just understood, everyone? So next, let's solve a problem about this reaction. I have taught you in the last session. This is a, what is the name of the reaction? Just think for once. So here also it will goes to a carbene intermediate. What will be happening here? This phosphorus will attack to the sulfur, giving us this type of carbene intermediate. Everything will be here. So carbene intermediate, and this carbene intermediate will undergo a rearrangement by elimination of carbon dioxide and giving us this alkene as the product. I think this was easy because you already have learnt about this reaction in the last session. Come to the next reaction. So explain the formation of the bicyclic product. Explain the formation of the bicyclic product. So you have to explain that it is, what is this? This is the, you guys may have understood, this is Grab's catalyst second generation. Grab's catalyst second generation, which is noted there as a C. So if Grab's catalyst second generation, what will happen? So let's start. Let's solve together as much you have learned till now. So it will first react with alkyne system and giving us this type of, first it will react with the alkene system and giving us this type of product. Okay, then let's see once recording is happening or not. So what will be the next? First, it will react with the alkene system, giving this type of complex, and alkene will be still there, and then it will attack to the alkyne system, giving us this type of moiety. Giving us um, giving us this type of moiety, and there will be still a double bond remaining with the metal character, metal carbene character, and this will add up to this double bond, giving us this. Understood, everyone? As much I could draw, I have drawn that. I think it's simple. Next is this one. So what is happening here? Again, in the same way, first the ruthenium catalyst will react with one of this carbene, and that carbene will one of the alkene, and that will attack. So the both alkene will join. If we go through the shortcut, the both alkene will join. So how many rings are there? 1, 2, 3, 4, 5, 6. So there will be a 6-member ring. There will be a 6-member ring. 1, 2, 3. Understood? With walk, there will be a below CO2. Understood? This will be the product. So what will be the product here? This is also the graph second generation catalyst. So again, it will react with the alkene. So in if there is a system with alkene and alkyne, most of the cases the alkene react faster. Alkene reacts fast than the alkyne. So there also first this will attack this alkene will react, and then this alkene then there will be a alkene metal type of complex, and this will add to this triple bond, giving generating a double bond. So let's write the 1 6. I don't know it's representing or not. So what will be next? Next, again this it will add up to this triple bond, and again we'll get this compound. It will add up to this triple bond, giving I have added all my previous lecture in YouTube. So if you have missed the lectures, anyone, so you can go and access from there. The channel name is Chanda Devnath PMRF NPTEL TAship. You can access those videos from here, and these videos will be also uploaded soon. And I have uploaded the slides through the NPTEL site, so I think you can access from there also. So what will be happening here? So first, there will be metal alkene complex will be metal carbene complex will form, and that will add up to this triple bond. That will add up to this triple bond. And this double remaining double bond will add to this double bond, giving us a tricyclic ring. So let's move to the understood everyone. I am just avoiding the substituents. It's a bit difficult for me to draw. When I will upload the slides, I will draw this properly, and you can understand. So if everyone can understand, like only this similar kind of examples is happening. Just next is this one. So this is the previous for my previous year's question. So what is happening here? So first they are given a alkene alkyne system for and a ruthenium catalyst, and they are given a double alkene system after that. So what will happen to a ruthenium? It will also always get a butadiene kind of system. I have taught you all these things earlier. Then it will add up to this double bond through here. This is called a cycloaddition reaction and giving us one of these products. So what will be the product? Let's see. So when it will add up, will get a butadiene kind of complex, and when the alkene system is added, there will be a 4+2 cycloaddition reaction, giving us this type of cyclohexane ring. So as this is concerted reaction, this will add up to from the same side. So restore keeping the geometry of the alkene intact. So see, both the substituents are in the same plane. Both the substituents are in the same plane as like here. Understood? Then now the next reaction is, so what will be the product from here? So see, I have given the solution also. You can see I have given the option. So what will happen? First N2 will get removed, giving us an alkene system. The cursor. So for N2 will get removed, N2 will get removed, giving us the alkene carbene system. Then this carbene will add up to this double bond, giving a cyclopropane ring. And when selenium oxide is added, we all know selenium oxide is is used to oxidize the allylic CH2. Allylic CH2 is oxidized to a CHOH. CH2 allylic CH3 or something, it will oxidize to give a CH2OH. So there is a allylic CH3 bond here, so it will be oxidized to give a CH2OH. So which one is the product? This one is our product. Understood? Next is this one. Here in this one, first the alkene, this carbene will generate and it will add to this aldehyde, giving us this type of ylide system, oxonium ylide system. And as this is two equivalent, see, you have to notice there is no reagent is there. So if you can say why what will you do? There's two equivalent, so one equivalent of aldehyde is still remaining. So what will happen? There will be a dipolar addition reaction that I have taught already earlier in this earlier of this lecture. So it will add up to this aldehyde, so cycloaddition reaction, and giving us the product. See? Cycloaddition reaction and giving us product. So which option is the again? So so this is the same, and our product will be this one. Our product will be this one. Understood? So let's discuss some new topics. So almost I have covered all the examples from, like, I have as much book I could, like I have taken the problems from some good books like Carisenberg, Caruthers, Claydon, Nance. So I have completed almost everything on carbene. So when you will get the slides, you will get everything from carbene. I think this much will be enough to solve any problem related to the carbenes. So this much will be enough. So let's talk about some new topic. This one I will discuss elaborately in the next session. But just to start, I will just introduce this topic for this session. So nitrenes. What is nitrenes? The nitrogen analogues of the carbenes are called nitrenes. As the with carbenes, both the singlet and triplet electronic states are possible. For nitrene state. For nitrene, the triplet state is usually the ground state. So generation, the most common method is the thermolysis or the photolysis of the azide. So what is happening? So when the azide is heated or light is given on the azide, this N2 will get removed and giving us this type of nitrene system. So these nitrenes can take part in different kind of reactions. So one is the characteristic reactions of an alkene nitrene is the migration of one substituent to nitrogen, giving an imine. So what is happening here? So first one, if the nitrogen will get removed, giving us a nitrene system like this. Giving us a nitrene system. Then one alkyl group will migrate to this nitrogen atom. This will come here, giving us this type of imine moiety. Understood? This is the famous characteristic reaction of nitrene. Next is aryl nitrene undergoes rearrangement. When it is aryl nitrene, like some aryl group is here. So in case of aryl group, there is also like similarly in case of alkyl, the alkyl group is migrating. In case of aryl group also, the ring bond will migrate. So after this nitrene formation, this ring will migrate from here, and it will come here, giving us this type of complex. When nucleophile is added, it will attack here, and a cyclic amine kind of system will generate. Okay. So we are now in the ending of the session. So a few intermolecular insertion reaction, especially in aromatic system, proceed in high yield. So when by similarly after N2 elimination, it will generate this type of nitrene system. Then like electrophilic substitution reaction, it will add here and N minus will generate, and then we'll get through aromatization we'll get this as a compound. Okay, so thank you everyone. This much was for this session. So I have another session last week, so that will be in the next week. That will be my last session on this topic. So if anyone has any question or any doubts regarding my videos or any slides, you can ask me. In my two of the videos are already in the YouTube. You can go and check. I have uploaded my slides also in the NPTEL. You can go and check. If there is any doubts or any query, you can ask in the feedback section or in the comment box anywhere. I will try to solve your doubts. And as I don't have much time remaining, because I just have one class in the next week, so after that this course will be ended for me. So if till now for from I just 1 week is there, so in this 1 week, if you guys just try to, if you guys just try to go through the videos as much as you can, or go through the slides. If you have any doubt or any mistake or anything I have done also, you can notice, you can tell me about that also. So try to, as much I can say that, to get a proper idea or a deeper understanding, you should have to solve the questions. Just watching the videos will not help you. It will not make you so this much for this now. So these are the recap. Okay, so thank you everyone. I hope you are understanding whatever I am trying to teach, or getting a proper idea. If you are not getting what is, so you can ask me any time, so I will try to solve those. Thank you. We'll meet in the next session. Good night.